Calipers with a serial interface or digital sensors like this are great for linear position sensing, but they lose their zero reference if they're powered down. So for that, you typically use something like an LVDT, but those are super expensive. So I was thinking, wouldn't it be cool if I could just measure the capacitance between two metal plates sliding over each other, and from that figure out the position? And it'd be even cooler if I could somehow just output a digital signal on one and see how that triggers the digital signal on the other. And ideally I'd have this working down to 1 picofarad capacitance. And rather than work out the math myself, I just kind of casually asked AI to see what it thought, and it just kind of gave back, dumb idea, this won't work. I basically have standing instructions for Google Gemini to tell me if it thinks it's a dumb idea, because, you know, it tends to agree too much on the whole. Basically, between voltage thresholds needed to actually go from 0 to 1 and input capacitance to the pins, it's just not going to be strong enough signal to actually even have something readable. But then I thought of a different strategy. So any pin that comes out of the Pico or any microcontroller is going to have some capacitance on there just from the internal circuitry. And on the Pico, I can enable a pull up or pull down resistor. So using both of those, if I just take a pin and have it configured as output high and then switch it to an input, it's going to take a while to drop. And so if I keep checking this line to see when it crosses from a 1 to a 0, that is something I can measure. And if I have additional capacitance on the outside here, even if it's very small, that will make this curve drop a little bit slower, so I can measure this capacitance. So I have it plotting on here how long it takes for the output line to drop, and it says 189 nanoseconds on the Pico. And if I just connect a simple piece of wire to the line that I'm testing this with, that already goes up by about 50 nanoseconds. And if I touch the wire, that's added capacitance, it goes up a lot more. In fact, I don't even have to touch it, I just have to hold my hand near it and it can sense the capacitance change from that. And I'm actually taking that measurement thousands of times for each one that I display and averaging those, which is how I can get it down to a tenth of a nanosecond, because the Pi Pico's clock is only 125 megahertz. And if I put a bigger thing on there, that can be incredibly sensitive, so just getting my hand near it already makes a noticeable change in how long it takes that line to drop. In fact, I don't even have to get near it, so if I just get away from it and then casually walk past it, every time I walk past it, you can clearly see that on the screen. And it works even through non-conductive materials, so if I just put my hand below the drawer, it can even sense its presence through the desktop and through the drawer. And capacitance measurements is basically how stud finders and pinless moisture meters work. They just measure the capacitance, just this one is designed to show you small relative changes, whereas this one gives you absolute changes and does a bit of calculations. And now on my workbench, and that workbench is a pretty thick slab of particle board. And if I stick my hand underneath here, it senses that. I'm not even touching the workbench. So if it works through the workbench, will it work through this floor, which is also pretty thick? So I jiggered up a metal plate on the ceiling connected to the Pico, connected to a Raspberry Pi, which I remotely connect to from my laptop so I can take that upstairs. So now I just have to wander around here while watching a computer, see where it is. Oh, aha, there's the spot. So the hot spot is in front of the laptop right about here. And if I just walk past there, yeah, definitely showing a signal. Even if I try to step over it, I see a bit of a signal. Okay, this is definitely a spot here, but even if I touch the floor a little bit away from there, it picks it up. So let's see, hot spot here, and I'll step over it. Nope, still caught it. I don't actually have to touch the floor for it to notice that I'm there. Now I had some difficulty getting that to actually work well, because in that particular spot with this plate, I'm picking up a huge amount of 60 Hz noise, and that totally swamps out the signal that I'm looking for, so I'm actually averaging over 5 full 60 Hz cycles, and that cancels out the noise. And I just realized what my problem is here. If I measure the AC voltage to ground with a voltmeter here, that measures 60 volts, and the reason is the adapter this is running off of doesn't have ground, so it just kind of uses the average of the hot and neutral, and with this thing floating around, it's not an issue. It's not going to zap me. There's no current on there. But in terms of measuring just the static sort of capacitance stuff like that, that 60 volts AC kind of messes it up. And when I had the Pi on my workbench, it was plugged into a monitor and it got grounded that way, but here it's just floating. So this setup works really well for measuring capacitance to ground, but I actually want to be able to measure capacitance between two plates. So I've got this plate hooked up to a GPIO line and this one hooked up to a different one, and I can slide them over each other to add some capacitance. So on the scope we have our sensing line, and first we drive it high and then we let it float down until it crosses the threshold, at which point we repeat this again. But you'll notice there's a little bit of a bumpiness right here, and that is from the second channel on the other GPIO line, and that one, let me just stop that, alternately, while we're declining here, drives it low or drives it high, and that always gives this thing a little bit of a bump here as it's declining, which changes how long this has got. And as I move my plates over each other, that bump becomes much larger. And now my measurement isn't so much how long it takes to get to zero, but what the time difference is between bumping it low and bumping it high. Because with a tiny bit of capacitance between these two plates, if the voltage on this one bumps from high to low or low to high while this one is declining towards zero, that adds to the voltage on here, which makes it take longer or shorter to decline to the zero threshold. So now with metal plates hooked up to those two GPIO lines, and my signal now is much stronger because I'm going for very close things, and if I stick my hand in there, it actually goes down because my hand is reducing the coupling between those two plates, because relatively speaking I'm a little bit grounded. But if I put a water cup in between, that increases the coupling by quite a lot actually. Although if I touch the water in the cup, that decreases it because once again, relatively grounded. And if I put the stick in between, that doesn't really change the readings very much, it's just not substantial enough. And even with a plastic bag on it, again, no change. But if I use an ESD bag, that actually increases the coupling by quite a lot, because this bag is ever so slightly conductive. Not enough for me to actually measure it with a voltmeter, but it definitely increases the coupling between the two plates. And this non-conductive piece of ABS pipe, if I stick that in between, also increases the coupling because this pipe has a dielectric constant, and that effectively shortens the distance between the two plates by just a little bit. Not much though, because if I just move this plate a little bit, that makes as much difference. It can also detect an empty glass sliding between the plates, or if you put some water in the glass, that makes for a much bigger signal. And now I've got a couple of pieces of tinfoil on the back of this ramp, and from that I can detect if something's sliding down. So now sending a screw down the line, and a nut, and even something non-conductive like this marble. As for position sensing, that works quite nicely, but it is of course sensitive to distance between the plates, so it requires precision in this direction as well. And on digital calipers, this problem is addressed by having a repeating pattern which gives you a lot of precision, and then the repeating pattern on a PCB that's facing it, which basically couples this pad to one of these pads here, and that's how they get such great precision. So here's a picture of one of those circuit boards that isn't black and magnified a lot, and we see a series of pads, and they're in groups of 8. So these 8 pads are connected in parallel to these ones, these ones, these one, etc. With the trace basically that's behind from here to here, here connects all these together. And that greatly increases the precision because now a small movement moves between a few pads, and with a lot of pads you get more signal. And that couples against this part here, so basically have these fingers that go across, and if the fingers are a little bit further away from the circuit board, well, the relative capacitance to the pads is still the same, so even if this board is at an angle or a little bit of distance, we still get a great deal of precision. So I think these many repeating pads on calipers is the way to go. That's how they manage to get 0.01 millimeter precision. But of course it means as you make large movements you have to count how many repetitions you've gone across, which means if you power cycle, you don't know where your zero is anymore. So if I had to make a precise linear position thing, I'd make it work like a caliper, and then maybe add a second scale that is much coarser and absolute, which tells me which repetition I'm actually in. But the thing is, I don't actually have a pressing need for a precise and absolute linear measuring gadget, so I won't be pursuing this any further. I was just experimenting, and it turned out to be really fun. Now I know for most of you this video has been way too technical already, but let's talk about the code a little bit. So this is a MicroPython program, and it runs on a plain Pi Pico, And most of the critical timing is done by this loop, which is actually instructions for the PIO state machine. So that does all the timing and actually load this quite a lot. So the PIO state machine on its own takes a full 8 readings and crams those into 4 words and pushes it out to Python so that Python doesn't have as much work to do. And then here I instantiate the state machine. I have another one for going the opposite direction. I don't use that very much. And then this code runs the PIO state machine. So first it creates an instruction word which tells it what to do for each of the 8 readings that it's supposed to do, sends it in this loop here, and then gets the 4 words out and has to do some adjustments because the result actually is what's left of the timeout. And then adds those up together and returns the average. And then this code here just kind of graphs it, either doing single-ended, that's capacitance to ground, or differential between 2 lines. And it has a sliding scale because I'm looking for very small changes quite a lot, but it can vary by a lot. So it'll automatically adjust the scale left and right if we go off scale. So I'll upload this onto GitHub, so if you have a Pi Pico, you can play with this. And the cool thing is, you don't actually need any sensors to hook up to the Pi Pico because the digital I/O lines are the sensors. How cool is that? Like not having to buy a sensor and being able to measure so much with it.